So this is the second of the worksheets for the Astrophysics Standard Level section. This is actually the May 2009 Paper 3 Time Zone 2 paper. So if you want to check that up. So the first question describes three characteristics of red supergiant star and state what is meant by constellation. So this is learning work basically. So I mean, there's the obvious one. They appear red. They are very large, extremely large, very large. You could say surface area or very large diameter. Obviously, with that very large mass. Very large mass. They have got a high luminosity. Not so much because of the temperature and amount of energy, but just because they have a very large surface area. And a constellation, it's important that you understand what this word constellation is. This is a group of stars that seem to be close together, and usually they make a pattern. In the past, people have made pattern when viewed from the Earth. They may in actual fact not be close together, may be quite distant apart, but when viewed from the Earth, they seem to be in the same vicinity, or certainly in the same vicinity of the night sky. Okay, good, so that was that. Now going to this question over here, we have the apparent magnitude. Now make sure that you understand you're working with magnitude. Apparent magnitude, not apparent brightness, is 1.1, and the absolute magnitude is minus 5.3. So this absolute magnitude, if the star is 10 parsecs away from the Earth, it would appear much brighter. It would be very bright, but it's actually further away, and so it's not so bright. Remember, the smaller the number, as it goes into negative, this indicates this over here is much brighter than the plus 1.1. So distinguish between apparent magnitude and absolute magnitude. This we've done before. We did it in the last question, the last paper. Apparent magnitude is a measure of how bright a star appears from the Earth or from an observer, and the absolute magnitude is the apparent magnitude of a star at a distance of 10 parsecs from the Earth. So show that the distance of Antares from Earth is 3.9 times 10 to the 7 astronomical units. Now, we have got the apparent magnitude and the absolute magnitude, so we're going to use this formula: m minus the apparent magnitude minus the absolute magnitude is equal to 5 log of d over 10, where this d is in parsecs. So we just put this in. This is our apparent magnitude. This value over here, this plus 1.1, is the small m, and this is your capital M. So we're going to get 1.1 minus, now don't make a mistake with this minus, put it in brackets, is equal to 5 log of d over 10. So that's going to become plus 6.4. Plus 6.4. 1.1 plus 5.3, 6.4. And we're going to divide that by 5. We divide it by that 5 is equal to log d over 10. We change it into our exponential form, so it's going to be 10 to the power of 6.4 divided by 5, and that is going to equal d over 10. So I multiply my whole equation through by 10, so I'm going to get 10 times that is equal to d. That 10 will cancel, and when we do that, we get a distance, a d, in terms of parsecs of 190 parsecs. Now I want to convert that into astronomical units. Now we know that one parsec is equal to 3.26 light years, and a light year is 9.46 times 10 to the 15 meters. So we multiply those two together. That will give us a value in meters, and we have that one astronomical unit is 1.5 times 10 to the 11. So we divide by that, and so we actually get that would be my conversion. So if I'm looking at 190, so if I change 190 would be that times, I'd have to multiply that by 190 times that whole thing there, and you get from that it works out to be about 3.9 times 10 to the 7 AU from that. Okay, so we would use this formula over here. Make sure that you can change your log form into your exponential form. Realize that this D is in parsecs. From that we can go further. Fine. Now moving down to this one over here, state the name of the method that is used to measure the distance. Now the type that we would use spectroscopic parallax or stellar parallax. Those would be the two that we would use. So stellar or spectroscopic parallax. You would use those two. It's relatively close. It's 190 parsecs, which is relatively close to us in universal terms. Now going into this one over here, we have got the apparent brightness. Let me go here. We've got the apparent brightness of Antares is 4.3 times 10 to the negative 11 times the apparent brightness of the Sun. Define the apparent brightness. Well, now you need to know your formula. So this is the power received per 1 meter squared, power received on the Earth. Okay, now using the answer to B2, show that Antares is 6.5 times 10 to the 4 times more luminous. So from B2 we saw that the distance for Antares was equal to 3.9 times 10 to the 7 AU, distance from the Earth to the Sun. And we also told that this Antares is that many times more luminous than the Sun. And we are wanting to, that's what we want to show. We want to show that luminosity. So we're going to do some ratios here. We know that we are given this over here, that the apparent brightness of Antares. So if we have BA over B of the Sun is 4.3 times 10 to the negative 11. And the apparent brightness is given by this formula over here. Remember, B is equal to L over 4 pi d squared, the distance. So now it's important when I do this that I label it so that we can just keep the two different objects that we're dealing with, Antares and the Sun, separate. So the BA is going to equal the luminosity of Antares divided by 4 pi the distance from Atari squared. And now we're dividing that BA, we're dividing it by BS, the apparent brightness of the sun. So I'm going to write it like this, the old primary school, elementary school way of writing division. That would be L of the sun divided by 4 pi d of the sun squared. Now, when I do that, when I divide, I'm going to invert and times. So what's going to happen is that we're going to change this into a times sign. This is going to go to the top and this is going to go to the bottom. When I do that, my 4 pi is actually going to cancel out. So we're going to get 4.3 times 10 to the negative 11 is equal to LA over LS, and here we're going to get ds squared over dA squared, like that. And therefore, this is what I'm trying to find. I'm trying to find this ratio of the luminosity of Antares to the luminosity of the sun. So that's LA over LS, and I cross multiply here, so that's going to be dA squared of Antares over ds squared times 4.3 times 10 to the negative 11. Now, we've already worked this out, haven't we? We worked this out over here, that dA is about 3.9 times 10 to the 7 at astronomical units. Now this is 1 astronomical unit, and that's 3.9. So we actually get this is equal to 4.3 times 10 to the negative 11 times 3.9 times 10 to the 7, and we're going to square that. And so when we do that, we get a value of about 6.5 times 10 to the 4 times 10 to the 4. Our luminosity, our ratio of the luminosity of the Earth, of Antares to the luminosity of the sun. So this sort of problem is you often get these in IB questions. You've got to work with ratios. It's very important to keep these things over here, to keep your subscripts in, so you know what you're dealing with, because otherwise it can become so messy, and you've got to work really carefully. Don't forget them, work logically, work carefully through it. You will have an opportunity to practice quite a few of these.